Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors from across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support and standardization, and open data and tools. ESIG is the lead on Pillar 1, and more information on the G-PST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the August monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and the research community participating in the G-PST. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we use the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG21 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, today's topic is on distributed restart, a project looking at doing black start of the power system using distributed resources. This is a topic that a lot of people are talking about, but not much has actually been done about it. Like many of the topics we have been discussing in this series, it is driven by the transition in the resource mix from one of large fossil fuel, nuclear, and hydro generation to one of largely inverter-based wind, solar, and battery resources. And here to tell us about something that is actually being done are Peter Chandler, with the National Grid Electricity System Operator in Great Britain, and Jack Haynes, lead engineer at SP Energy Networks. We heard from Pete back in 2020 when the project was just getting off the ground, and now we will hear again from him and Jack just as the project is coming to a close. Pete has worked for National Grid System Operations for 30 years and is a power system manager within the Electricity National Control Center. Pete also leads the Distributed Restart Innovation Project and is accountable for all aspects of the work. Jack is the lead for the Power Engineering and Trials workstream on the Distributed Restart Project. He was responsible for delivering the most recent world-first live trial at Red House in Scotland, using the Greenspan battery energy storage system with the grid-forming inverter as the anchor generator. I feel very fortunate to have Pete and Jack here with us today. The Distributed Restart Project began in 2019 as a partnership between National Grid ESO, SP Energy Networks, and TNEI, an energy consulting firm, with funding from Ofgem, the energy regulator. The project is a world-first initiative exploring how distributed energy resources such as biomass, wind, hydro, solar, and batteries can be used to black start the electricity network in the unlikely event of a blackout. The webinar will cover details of the live trials undertaken over the last few years, coupled with information on the necessary organizational systems, telecoms, procurement, and compliance activities needed to make the transition to business as usual. I greatly value the contributions of the NGESO and SPEN to G-PST and the industry, and I look forward to what Pete and Jack have to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG21 to ask your questions. And now, without any further ado, let's go ahead and get started. Pete, I'll now turn it over to you.
Thank you very much, Charlie. That's an absolute pleasure to be presenting to you all today. So as Charlie says, my name is Pete Chandler. So I'm a power system manager for National Grid Electricity System Operator. I've just finished a shift in the control room, so it was all interesting, all good. I had the pleasure of presenting back in 2020, as Charlie described. Very different times then, during the height of COVID. So things have moved on, and we've done a lot of work on this project. So it's a pleasure to be here to share with you today. Before we sort of go into the sort of detail, we've got a video for you which will describe what we've been doing for distributed restart. So over to you, Jack.
In 2019, National Grid Electricity System Operator, SP Energy Networks, and TNEI began a 3-year project to explore a completely different approach to electricity system restoration. An innovative idea that would use distributed energy resources, including renewables such as wind, solar, and hydro, to restore power to the networks for the first time. We call this distributed restart. At the beginning, it was just a theory. Now,
Excuse us, everybody, just a small technical hitch.
it's taken 3 years of intense collaboration, with many different skills and disciplines involved, and extensive engagement with stakeholders across the industry. We have developed the technology and demonstrated that it's possible, producing specifications for power networks, control systems, and resilient telecoms services. We ran desktop exercises to guide organizational design and demonstrate how training might be delivered. We ran mock tenders to inform the design of a new commercial service. And at all times, we ensured we kept the industry up to date with our progress and findings. At our world-first live trials, we proved the ability of distribution-connected hydro and steam generators to initially start up and energize their local distribution and transmission networks, right up to 400 kV, the highest voltage on our electricity networks. This included powering up turbines on wind farms within the isolated test network. We set out to bring distributed energy resources into electricity restoration, and we succeeded. This could mean, in future, diverse suppliers replacing the fossil fuel power stations, providing more competition and opening up the marketplace. But we've taken things further than expected. We've designed, built, and tested an automatic control system to make fast and complex balancing decisions at distribution level, while dealing with potentially hundreds of distributed energy resources. This supports a new role for distribution network operators, with a new command and control structure, processes, and systems. Although our 3-year project has successfully completed, that's just the first step. We need to transition everything we've designed, tested, and demonstrated into a viable commercial service. We must meet a new electricity system restoration standard by the end of 2026. We now know how we can comply with it, but we can't do it alone. We're looking forward to working with hundreds of partners across the industry to implement it. Join us as we build a new way of restoring our electricity network. Distributed Restart.
So I hope you enjoyed that video. Apologies for the glitch in the sort of technicals. Give you a bit of an insight into what we've been doing. So just building on that, some of the themes within that video. So the project was launched back in 2019. It was an innovation project, partnership between National Grid Electricity System Operator, Scottish Power Energy Networks, and TNEI. And we were looking at the options around restoration or black start, and looking at the potential ability to restart networks from distribution systems, utilizing a whole range of different sort of technologies. The conventional approach that we use here in Britain is similar to lots of other countries, where effectively we restart the network via energizing the transmission system, utilizing very large fossil fuel power stations contracted for sort of delivering restoration service. Energizing the transmission system, linking up into and establishing what we call a skeleton transmission network, and then energizing down to the distribution networks. Distributed restart is looking at doing it in a effectively flipped way, effectively energizing distribution energy networks using distribution energy resources, wind, hydro, biomass, and batteries. So effectively a bottom-up approach for restoration as opposed to sort of top-down. No one else in the world does this, or certainly didn't do it when we started this project. And one of the big objectives is to open the marketplace essentially for renewables and how they can participate in restoration going forward. So next slide, please. So the way we structured ourselves, we were structured into sort of 3 main work streams. The first work stream, power engineering trials. This was our technical work stream, looking at all the sort of technical aspects associated with restoration, distribution level, protection, earthing, short circuit levels, energization, all those sort of things. The modelling around that and the live trials, which Jack will go into a bit more detail in a second. The second work stream was organisational systems and telecoms. So this was looking at how we organise ourselves on the day, all the different parties that participate in restoration, how we organise ourselves and establishing a sort of command and control structure. And the third work stream, procurement and compliance, was looking at the commercial aspects. How can we turn all these sort of technical challenges into an opportunity for people to participate and provide commercial service, and the regulation around all of that. So those are the sort of 3 main work streams. The next slide, please. So building on that, power engineering trials. So what we delivered, so our achievements, if you like, what we delivered. So we proved through lots of kind of modelling on our chosen networks that restoration from distribution networks and distributed energy resources was possible. So we were looking at energising transformers, energising lines, all those aspects around protection as well. So we have established a functional specification for how it can be done. We also designed and built essentially with our project partners, GE, a prototype control system that would essentially grow a power island from scratch, and energize other elements of the power island, integrate other sort of generators, and ultimately be able to synchronize up to sort of transmission level. So Jack will take you through a bit more detail on that. And that was kind of everything from that work stream. Organisation, systems and telecoms. So we established command and control structure for that work stream, for that involving the DNOs. The DNOs, the distribution network operators, essentially in charge of the distribution networks in Great Britain. So we've created a new role for them, effectively in control of their power islands once we are restoring their networks. So we'll take you through that in a second. We also established a functional specification for a resilient telecoms system. So telecoms are very important. We need to be able to talk to each other in a kind of a restoration event. So we've been able to do that and do sort of resilient telecoms networks. We've established a sort of functional specification to that work stream of how we're going to do that. So moving on to the third work stream, the commercial work stream. So we've kind of built the models, how the commercial service would look like. We've worked with all our industry stakeholders, and they helped us design the commercial service and the way that we would procure for that commercial service. And we've tested that through what we call a mock tender. So we've actually gone through a mock tender event of how we would procure services. The regulatory arrangements as well, we redefined what those might look like, and we created sort of drafting texts for the industry codes that will need to change to make all this possible. So in total, this talks about 27 reports and briefs. So I think that's probably higher now. We've got probably up to about 30 reports we've got now, and I think we've got a couple more coming in October. Lots of engagement events, lots of design specifications, lots of sort of detail work. All of our knowledge and dissemination events, including some podcasts we did during COVID. Loads and loads of material, which we've shared on our website, and we can direct you towards that at the end of the presentation. Next slide, please. So a bit more on organizational systems and telecoms. So I mentioned about command and control. So in Great Britain, the electricity system operator is responsible for restoration. So providing the restoration services, essentially through contracts with generators. We're also responsible for how restoration would work on the day. So responsible for the strategy of expanding the power islands, linking the power islands up and restoring the networks in GB. So electricity system operator currently does that. As I mentioned earlier, it's very much a top-down approach, energize the transmission system down to distribution level. So the command and control structure that we designed for distributed restart was essentially putting the DNO, the distributed network operator, in charge of and responsible for restoration of their power islands on their networks. We've called their power islands on their networks, we've called them DRZs. So what that acronym stands for is Distribution Restoration Zone. So when you see DRZ, what it means is a power island on a distribution network system. So the DNO would be responsible for restoring that power island, that DRZ. So the ESO would still be responsible for declaring a national emergency and declaring a national sort of black start event, and would still retain the responsibility for national and regional strategy for restoration. So we would continue with our top-down approach. We would also then instruct the DNOs, the network operator companies, to effectively go with their restoration plans to establish their sort of power islands to provide this new bottom-up service. So essentially you'd have a top-down and bottom-up service working together, ultimately to accelerate restoration. So that's what the command and control structure looks like now. The transmission operator companies essentially provide the transmission network. The DNOs are the distribution companies, so they would be doing a lot of the hard work and restoring demand. And now we've got the DERs, the generators, distributed energy resources generators as well, involved as well. So a lot more operators. So the command and control structure we designed it with all those companies on your right-hand side, all their inputs, which we were very grateful for. And we ran a series of desktop exercises over a number of months in the summer of 2021, I think it was, to effectively road test what that would look like utilizing a simulator. And we got some good insights and some good feedback around that. Next slide, please. The second deliverable from the main deliverable from the work stream, as I mentioned, was the telecommunications. So we established a telecommunications functional design, take into account all of the existing telecommunication infrastructure. We worked with industry partners at telecommunication experts, government, telecoms regulators, and the DNO companies themselves. And we got loads of good input from them, and we built this functional specification. And that functional spec is on our website, which you can visit and have a look at. It was important that we built in cybersecurity as well, and resilience into that telecoms design. And we've also the diagram that you see essentially is a diagram of how the telecoms network would work, all the communication paths, and the DRZC, the effective automated control system, which Jack will talk to you about, how it all fits together. So I won't go into too much detail, but essentially we've arrived at a solution, functional specification solution for all network operator companies now to utilize and build on their existing telecoms infrastructure. Next slide, please. The procurement compliance deliverables. This is the commercial work stream. So we built the commercial design, how the commercial service would look like, how we would procure for that commercial service. And effectively, we've road tested it through a mock tender. The ESO would retain the overall responsibility in the first instance, around leading the procurement activity. How all this would be funded. So we've agreed how this would be funded. The commercial services around the generation would be funded through contracts with the ESO, and the remuneration around network assets, as a fair amount of network assets required to make this work, would be funded through regulatory price control arrangements. And interestingly, all the technical requirements required for restoration, we split those up. So now we've come up with a what we call an anchor generator. An anchor generator is a generator that can self-start and can provide a voltage reference. And then we've called top-up services, so other services such as short circuit levels, inertia, fast megawatts, reactive power. All those different elements could be provided separately through what we call top-up services. So our commercial arrangements are out there, which you can have a look at. Effectively, you can go and procure for all these things separately. And the ESO would then, under its procurement lead responsibility, would be responsible for assessing the collective, if you like, of those separate services to link together into a complete restoration service for a particular power island. And the codes, the legal text around the codes, all the sort of legal requirements required to make this work are being passed through a code modification working group at the moment. So you can have a look at some of those recommendations. So that's it for me for the time being. I'll hand over to Jack. We'll take you through some of the work on the live trials.
Hi everyone. Apologies for the delay there. As Pete introduced me, I'm Jack, the PET workstream lead for Distributed Restart, and I was responsible for delivering the most recent trial that was undertaken at Red House substation in Glenrothes in Scotland. But before going into the detail of the trial, I just wanted to kind of really drive home the motivation for delivering the project. And it was ultimately to try and drive down the time it would take to restore the network in the extremely unlikely event of either total or partial shutdown of the UK grid. I'm sure it's not unique to our grid, but if we did experience total blackout, that we'd probably be looking in the region of around 5 to 7 days for full system restoration, which would obviously be catastrophic for the UK or indeed any network that experiences an outage of this time. So, as Pete alluded to prior, the main reason for that is because we utilise large synchronous fossil fuel generators a lot across the UK to gradually get the transmission network re-energised to eventually trickle the supply down to customers. That purely top-down approach. So what we wanted to do was complement top-down approach with the bottom-up approach as well. So by utilising a series of distributed energy resources, whether they be wind, biomass, hydro, batteries, solar, to get much smaller pockets of the network online far more quickly, get customers online in as quickly as 24 hours, and then ultimately grow those power islands to the point where we can then resynchronize with the intact grid. So there was a piece of legislation passed in the UK that has mandated that from 2026 onwards, if we did experience a black start, that at least 60% of demand would need to come back on within a 24-hour period. And I don't think that we would be able to meet that target without the kind of learnings and BAU transition from distributed restart. Coupled with the kind of main deliverable, there's a number of sub-deliverables as well, and that we can encourage further renewable generation, and that there's another revenue stream for these generators to be able to monetize by being on standby to be able to provide the restoration service provision and contribute to the distributed restoration zones, whether as either through being the anchor generator itself, so the initial startup generator, or through top-up generation, and that when you grow the island to the point where it can start to develop further generation, that they have the ability to do that. So as Pete alluded to, there was kind of 2 earlier trials that were completed last year. The first was we utilised a series of hydro generators in Dumfries and Galloway in the south of Scotland. A series of 13 MVA generators connected at 11 kV to energise a test network that was isolated from the main grid all the way up to 275 kV. And one of the key figures that was measured there was the block load pickup capability of the assets. So that's the single instantaneous load that we can add to the power island without the island losing stability. So that figure is key in terms of giving us an understanding of how much demand we can bring on from the resources that we've got at our disposal in the power islands. Then similarly, later on in 2022, the Stevenscroft biomass generator was utilised to energise all the way up to 400 kV. This time it was a 53 MVA unit connected at 33 kV. And again, the block load pickup capability of the asset was measured there. So up to this point, we demonstrated the ability of a series of synchronous generators to energise all the way up to the highest transmission level that we have in the UK. But what we hadn't been able to, or hadn't had the opportunity to demonstrate, was an inverter-driven non-synchronous machine to act as that anchor generator in the power island, which is where the extension to the trial or the series of trials as part of the Distributed Restart project came in, and that was to utilise a battery energy storage system, in our case, to act as that anchor point and grow the power island to energise both the local distribution and transmission network, and also add an additional DER to the mix to act as that top-up generator. So you can see a snapshot of the test network that we had set up for the series of tests over the 2-week period in the bottom left-hand corner there. But I've kind of boiled it down to its main parts, in that The anchor generator, as I mentioned, was an 11.6 MVA battery energy storage system that had been retrofitted with grid forming technology. So it's unusual for battery storage systems to have grid forming technology. That was designed as part of the project. We utilised a 5 MVA load bank that was supplied by Greco, and the purpose of this was to mimic primary demand coming on and off during the series of tests, because we didn't want to affect any genuine customers, and thankfully we didn't experience any outages during the trial period. The distribution assets that we had set up as part of the test network were a 24 MVA primary transformer connected at 33 kV or 1133 transformer, and that was connected via an underground cable at Red House. And then we also had a 10 MVA transformer connected via an overhead line. As I mentioned, the additional resource that we had that acted as the top-up generator in our case was a 3 MVA solar farm in Midabal-Beggy. And then in terms of the transmission assets that we were looking to energize, back energized from the anchor source, we had a 90 MVA grid transformer also co-located at the Red House substation, and then also a 10.6 kilometre 132 kV line out to the neighbouring Gleniston substation. So pleased to communicate that the tests were really quite successful. The BESS performed excellently in terms of energization characteristics. So we've proved that the BESS is very effective at starting, maintaining and controlling power islands very effectively with the added support of a diesel generator or not, that it can energize both distribution and transmission assets, both transformers and lines, and is much more effective at doing so when utilizing a device called a point-on-wave relay, which I'll provide some more detail on in a subsequent slide. We also measured the block load pickup capability, that figure I talked about earlier, so the instantaneous load that we can bring on in one go. So how many houses, essentially what that boils down to, so how many houses can we turn on in one go with this device acting as the anchor whilst the island maintains stability. Again, I've got some more detail on a subsequent slide, but it was found to be far superior when compared to a synchronous machine of the same size. The DRZC, which Pete alluded to, the distribution restoration zone controller, we utilize that functionality to automate a lot of the control in the power island that would otherwise be manual, because you can imagine a genuine black start scenario, and Pete will know better than me that the pressure on the control room is going to be immense. So the more that we can automate, the better, in that it's much better to have a power island that's ready to energize customers as opposed to one that's still building up. As part of the DRZC, it has checksum functionality in it to allow it to resynchronize the power island that we've generated with the intact grid. And then one of the subsequent tests we did after reconnection to the grid was utilizing the series of assets that we had in the island as a dynamic virtual power plant. So what I wanted to do is just draw your attention to some of the highlights from the tests. So the first one was that key figure I talked about, so that block load pickup capability. So what's the maximum load we can switch on in one step whilst the island maintains stability? So generally the threshold was, the understanding of the threshold was that how the frequency deviation didn't drop below 47.5 hertz. Now we had a 4 megawatt load bank at our disposal, and we gradually stepped the load bank up in higher and larger steps, and it was pretty immediately apparent that the BESS was able to cope with load steps of those sizes very well. You can see in this example here that where the orange arrows are pointing to, that's the point where the instantaneous load of 4 megawatts was implemented. Within about 2 or 3 cycles, so around 60 milliseconds, the BESS has already recognized the additional load present in the island, modulated its output to cope with that, and then settled at the expected voltage and frequency as per its voltage and frequency droop control settings. And you can see it only deviating to around 49.5 hertz in this instance. Now, the BESS, its capacity itself was only 8 megawatts, We stepped 4 megawatts. If we had a larger load bank at our disposal, then we could have done larger steps. But it's from the analysis we're doing as part of the report, which will be published towards the beginning of October, it's apparent that the true block load capability of the BESS is probably towards or tending towards its full capacity, which when compared to a synchronous machine is considerably better. You know, you'd expect to maybe get about 20% of a block load pickup capability of a synchronous machine, whereas here we've demonstrated that you can get at least 50% out of the BESS, but in reality it's probably closer to its full capacity. Another highlight was the synchronization of the intact, so the power island that we generated with the intact grid. So what you can see happening here, the yellow line on the graph here is the grid, and the light green line is the power island. So what you're seeing is the voltage, frequency, and angle difference between the grid and the power island that we've got. So the DRZC is monitoring what's happening on both sides. We deliberately pushed the voltage and frequency of the island away from the grid, and then at about 11:19 or so here, you can see that the DRZC is then armed to start tracking the voltage and frequency of the grid. So it's using the load bank and the BESS to push the voltage, frequency, and phase angle of the island to be closely in line with that of the grid. And then when it's within a particular threshold, in our case it was 5%, as highlighted by the orange element here. That's when the DRZC armed the circuit breaker for closure, and then you can see following the closure that the voltage, frequency, and phase angle are in line, so left behind a kind of seamless closure following the checksync functionality. And then the last highlight I wanted to draw your attention to was when we were energizing the transformers. So one of the phenomenon that kind of causes issues when back energizing the network, like we were doing in this case, is the inrush current of the transformers. So the inrush current causes a reactive power draw and pulls the voltage down. So we had installed a device called a point on wave relay, which the way it works is by measuring the point on the wave of when the transformer that you're looking to energize is de-energized. So it memorizes that point, which is driven by the remnant flux in the transformer. It then measures the point on the wave of the live side, and then when understanding the closure time of the circuit breaker, it closes the circuit breaker such that the point on wave of the live side matches the point on wave of the dead side, such that the inrush current is mitigated as much as possible, and you don't see a voltage deviation, or as much of a voltage deviation as when you're attempting a hard switch or a switch without any mitigating technology. So the two switches you're seeing on the left, highlighted by the orange circles again, that's when we attempted without point on wave. So you can see the voltage at 33 kV being pulled down to about 29 kV as a consequence of the inrush current of the transformer. But then when we utilize the point on wave, as demonstrated, that we did 3 switches, as demonstrated by the orange circles to the right hand side there, you can see that it's almost negligible, the voltage deviation, and that it's only pulling it down in the worst case to about 32.8 or so kV. So the point on wave was a really effective device that we utilized for the duration of the tests. And whilst we did have some issues and trips as a consequence of either under frequency or under voltage when not utilizing the point on wave, we were always successful when utilizing the point on wave relay. So I think it points to the fact that if DERs are going to reliably and securely contribute to a distribution restoration zone, that having a point on wave relay installed is certainly something that should be encouraged. And you can, it's quite plain to see the results on this slide. So this is a repeat of the earlier slide, just to round up what I'd been saying about how successful the tests were. We were probably surprised actually by the performance of the BESS overall and how quickly it was able to react to issues and instances of generation demand changing within the power island. And that certainly the foundations have been laid for battery energy storage systems to be used not just in the UK but around the world as really feasible restoration services providers. So I'll just hand back to Pete at this point.
Thank you, Jack. So that's brilliant. That blows me away, actually, every time Jack takes me through that as a control engineer, to see sort of converter connected technologies working together to grow and establish a stable power island, which then can synchronize to the main grid. And we've tested it, and we tested the automation to be able to do that as well. It just blows me away. So thanks very much, Jack, for that. So going forward then, so the project itself is coming to a close. We've got to write up the results from that last trial, which we'll be publishing in October, and then the project will draw to a close. We'll have all of our material will still be available online for you to sort of take and read and use. So it'll all still be there. How are we going to progress some of the learnings, in fact, all of our learnings, into more of a BAU world? So there was a question on Slido, I might as well sort of take now, about mock tenders. The way that restoration services are essentially provided in Britain at the moment is through a commercial arrangements. So bilateral, used to be bilateral, now it's through what we call it sort of tender arrangements. Essentially, commercial agreements are struck with the electricity system operator and a generator to provide a restoration service. But before you get to that point, all the sort of technical requirements are published, and we invite people to register their own interest. And if people are serious about providing a service, we'll ask them to provide us a formal engineering piece of work to prove that they could physically do a restoration service. And through a sort of tender process, where generators essentially competing against each other within regions within Britain, we'll establish our needs, and then we will contract accordingly with providers. So essentially, we've got 6 zones in GB for restoration. We've got to split up into sort of 6 zones. That's how we're structured at the moment. The intention is to integrate distributed restart into those commercial arrangements. So essentially publish a set of requirements that would be relevant for transmission connected resources, but also distribution connected resources. And then it would be for providers then to demonstrate they can meet those requirements. As I say, it might be a large generator, it might be smaller providers providing only certain elements of the technical requirements. And then the ESO, the electricity system operator, would assess how that would work together, whether it is as a single entity or whether as a collective in a local area. And again, under a sort of tender arrangement, there will be potentially generators competing against each other. And again, we will assess our overall need for a particular region, and then we'll award a contracts accordingly. So the intention is to integrate this distributed restart solution to our BAU commercial arrangements to provide restoration services. On top of that, the government in the UK has established a ESRS, Electricity System Restoration Standard, a brand new standard. So all the technical, commercial, industry requirements around pulling together essentially, so that we can meet a restoration standard. And that restoration standard, Jack mentioned, it's about timescales. It's about getting volume of customers restored within timescales at a regional level and a national level. So the intention is to integrate the distributed restart commercial services in our regional tenders for the southeast and northern regions. The northern regions is essentially split into sort of 3 sort of sub areas: the northeast, the northwest, and Scotland. So essentially, 4 of our 6 regions are being covered, and essentially we've offered. We went out with expressions of interest for participants, and we've had quite a large interest from 7 different technology types. including wind, batteries, solar, and hydro, where traditionally we would only have expressions of interest back from 2 to 3 technology types. So we've opened the marketplace, we've opened the sphere for restoration, and the intention is to start delivering some of these distributed restart solutions in parallel with the more traditional restoration solutions within these regions, to go live back end of 2025, so just over 2 years away from now. So that sort of draws to the close of how we're going to take forward our sort of commercial procurement arrangements for restoration. But all the sort of technical bits and pieces and organisational services will, all of that will be taken into account when we are assessing how that service would work. And ultimately, all the players in this, whether it's the transmission companies, distribution companies, the generators at distribution level, or the electricity system operator, essentially we would agree agreement. We would have a restoration plan for that restoration, for each individual restoration zone, which each party will have. So we would agree those plans, and all the sort of technical requirements and organisational requirements would be included in those plans. So again, we've drafted some templates, what those plans might look like, so we can have a look at those on our sort of website. Next slide, please. So I think that draws to a close our presentation for you today. The webpage I've been referring to is, you can type into your browser distributed restart. It should come up. We've got an email address as well. So if you've got any questions you'd like to ask us, you could use the restart@nationalgrid.com, and we'll monitor that sort of Dropbox account and take your questions and attempt to answer them. We've got some FAQs, frequently asked questions, on our webpage as well. So we've been asked lots and lots of stuff over the last 3 to 4 years, lots of material there, lots of answers as well. So please have a browse, and yeah, we look forward to helping you wherever we can.
Thanks so much,
Charlie, for questions.
And Jack, a very, very impressive piece of work, very comprehensive and very thorough. Really amazing to see, just like you said, starting up from the distribution system to the other end is quite an accomplishment. Before we get into the Slido questions, I have one question I want to ask, and that's just about the role of wind and PV. I noticed that you did it with the battery. It was a 3 megawatt PV plant available, but what's your sense of the ability to use the wind and the solar with or without a battery, operating at full power or not at full power? What's your sense of the challenges associated with doing it with wind and PV, and how do you see that playing out?
I could probably do that one, Pete. No, it's a good question, Charlie. I think we utilized the solar farm at the Red House trial as a top-up generator, and when we did the series of trials down in Dumfries and Galloway, a wind farm was also brought on as the top-up generator as well. So obviously, due to the intermittent nature of renewables, it's difficult for them to act as the anchor. But the tender that's being run, as you know, the complements distributed restart, is tendering not just for anchor generators, but for top-up generators as well. So those that, in the event of a black start, would contribute to the DRZ's, the distributed restoration zone, by adding additional resilience and security. There is actually another innovation project which is kind of just getting off the ground at the moment, called Blade, which is investigating how we could use large offshore wind farms as anchor generators. But that's certainly in its kind of early stages of development at the moment. So in the short term, I would suggest that solar and wind are going to be utilised as top-up generators only, but depending on the results of Blade, in future, large offshore wind farms could also be anchor points as well.
Yeah, very exciting. Thank you. Okay, looking at the Slido questions here. The top one there, is there a recommended ratio of grid forming to grid following units required for a successful black start restoration?
Another good question. Yes. So due to the fault level in feeds that we utilized during the trials with the synchronous generators, there was a 3-to-1 ratio of grid forming to grid following. Generally because of the energization associated with trying to get the wind farms off the ground, particularly. In the case of the inverter to inverter, with the BESS and the solar farm, that didn't exist, and it was closer to a 1-to-1 ratio would have been acceptable. But it really depends on the characteristics of the island, but generally the characteristics of the generation that's going to be acting as the grid following asset. And so with the tender that I mentioned earlier, we're doing detailed technical investigations as part of each of the prospective DRZs to make sure that the top-up generators would be able to effectively contribute and have the right ratios in place.
Yeah, very good. Thank you. Next question. Do the batteries have to hold a minimum state of charge at all times, i.e., what happens if the blackout happens when the batteries are drained?
It's a good question again, and it's one we're still playing with.
I could probably take that one. Yes, they will. We have a similar issue at the moment. We've got a pump storage plant contracted for sort of restoration in Britain at the moment. Similar concept. You have to have a minimum amount of water contracted to be able to deliver the service. So yes, you'd have to have a minimum effective charge to be able to provide the service. That would be essentially part of the contract negotiations and the how we would sort of tender for that service. So yeah, that could be built into a contract. The beauty of a battery or any energy storage system is that you can utilize it in two directions. You can use it potentially as a in this case an anchor generator. But once you've got a stable power island established with other resources integrated, then you can use it as a source of demand as well. So, yeah. So yes, to the answer to the question.
Yeah. A follow-up related question that just popped into my mind, Pete, is if the incentive from the distributed restart procurement is large enough to incentivize the installation of mostly grid forming batteries in the future.
Yeah.
A big enough incentive?
There was so in the UK we had last year, I think it was, one of our industry codes was modified to allow grid forming sort of technologies and the rules around that. So that's now live. You're absolutely right though, Charlie. With the right incentives, you can incentivize people to provide sort of different services. So yeah, I would agree with that.
Yeah. Okay. This next question here, I think, is just maybe a follow-up. Can you provide a link to the name of the Black Start legislation that drove some of these efforts? Maybe we can include that in the follow-up Q&A at the end. Did you consider using some battery energy storage as a load during Black Start to match up with the generator output? Did you consider using batteries as a load?
Sorry, just repeat that, Charlie, just so I understand.
Yeah, I'm not quite following it myself. Did you consider using some battery storage as a load during Black Start to match up with generator output?
Yeah, so when we turn the solar farm on, yeah, so as part of the test network, we not only did we have the solar farm, but there was a diesel generator there to support making sure that we had sufficient state of charge for the duration of the trials. So we did do 4-quadrant testing of the battery, so pushing it through all 4 quadrants of P and Q output. So there was times where it was charging both reactively and in terms of real power output. So yeah, we as part of the report that there'll be a section in there about how the battery performed in the 2 control functionalities that we used to do that. Nice. So yeah, we did utilize it as a load.
Okay. Is this point on wave relay for the transformer a commercially available product, or was it developed specifically for this application?
No, it's a commercially available product. It's used in the generation industry and has been for a number of years. It is a bit more of a bespoke or rare device as such, but It is commercially available, and we procured it as part of the project. It wasn't developed specifically for the project. And the slides I demonstrated earlier, its ability to provide a reliable and repeatable output was clear. And yeah, it was invaluable for especially being able to energize the larger assets.
Okay. And a related question, did you have to modify the protection settings, particularly for the inverter, to cater for the high inrush current when energizing the transformer?
Yes, we did, in short. So there was a protection assessment that was done by one of our teams prior to the testing to make sure that the protection settings would have. A lot of the issue was around there being enough fault current to trip the protection. But certainly, there was a detailed analysis done to make sure that the protection settings that we implemented for the trials would be sufficient. We were lucky enough not to experience any faults during the trials, but we did experience a series of trips, predominantly on under voltage and under frequency, as a consequence of the inrush. And we'll be making suggestions for protection amendments as part of the report.
Yeah. Question on the economics here. Are the battery storage facilities cost competitive versus synchronous machines for black start services?
I can't comment on that. As I say, we're currently undergoing our technical and commercial assessments of those regional tenders in Britain at the moment. So we think that there's certainly a lot of battery providers out there, and in a sort of competitive environment, we hope that they will be cost competitive. Not just battery though. I mean, other renewable sources as well. That's partly why we were asked to look around the commercials within this project, because the costs for restoration, certainly in Britain, were escalating quite alarmingly with the closure of a lot of the fossil fuel generators. So I would hope that they are competitive. I can't tell you outright that they are at the moment.
Yeah.
We'll see in the next 12 months, I think.
All right. There's a lot of hybrid facilities going in the US, hybrid PV battery or wind battery facilities that I think would probably be good candidates for that kind of service as well. There's a lot of voting going on, so the questions are jumping around, but I'll try to take them in order here. Do you find that the behind-the-meter resources, e.g. rooftop solar behavior, complicates the restoration?
Do you want me to take that one, Pete?
You can do. I don't know how to answer it.
Yeah, we haven't, because we utilize the load bank to simulate the customer demand. We haven't actually affected any genuine customers for the duration of the trials. I think that's probably one to take away, because it's a good question. But yeah, I imagine any volatility on the network. So when we're trying to restore any figures that we can't measure or have reliance on, would certainly cause complications to the restoration process. But yeah, we'll provide a more detailed answer on that by email if that's okay.
Sure. Markets. Which electricity market mechanism can support the black start functionality? I think you covered that, Pete, but maybe.
Yeah, just to build on that, I'm not sure if everyone realizes that certainly in Britain, we operate a balancing market where generators and sort of demand sources sort of agree contracts, and the electricity system operator is essentially the sort of balancer of electricity supply and demand. So there's a market for that. There's also all the ancillary services as well, like reactive power, stability, restoration, and thermal as well. So there's lots of ancillary services that we contract for. Restoration is part of that. So there's lots of markets in Britain. Across the world, it's different. I realise that. Yeah.
Okay, here's an easy one for you. Do your anchor generators also have to be able to establish frequency as well as voltage? And if yes, how much does that restrict your pool of possible anchors?
Yeah, in short, the answer is yes. But I think in terms of synchronous machines, they're generally covered. But the grid forming technology that was installed as part of the trial certainly gave us the ability to dictate the frequency, and frequency control for the duration of the project or the trials was key. I'm not aware of what the portfolio looks like in the UK of voltage driving grid forming technology as opposed to voltage and frequency. So it's something we'd have to do a wee bit more analysis on. Pete, I don't know if you've got any more info on that.
No, sorry.
Okay, I'm going to take one last question. It's about the top of the hour, but this is an interesting one. What has been the response from the distribution network operators? This seems like it would be a major increase in responsibility for them.
So there's been a lot of interest, actually, and a lot of input in all of our work streams from the distribution network operators. So we've been working with them around the commercial arrangements. We've been working with our regulator as well to provide a means to fund some of these things. There's a lot of sort of network assets that potentially are required to establish a stable power island, things like earthing devices, the controller system itself, changes to protection, load banks, point and wave relay, things like that. So the network assets side, obviously they are regulated. So the DNOs are interested in the funding arrangements around that. We've got a route for those for that funding to now be taken forward in their normal sort of regulatory price controls, which is a big success. The direction of travel is around more and more distributed energy resources at distribution level, and also direction of travel is around distribution system operations as well, and automation around that, and smart control. So it all kind of fits together quite nicely, and there's a lot of interest from the DNOs around that. So I'd say they're broadly positive around it, but we'll see as we go forward into the sort of next stage of integrating to BAU how it works for real.
Yeah, the direction is clear. Okay,
Yeah.
we're just a little past the top of the hour, so we're going to need to wrap it up. I want to thank Pete and Jack for this really informative webinar on the world-leading results of the distributed restart project. A very impressive piece of work. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We appreciate your engagement, and if you'd like to stay engaged, I would invite you to participate in the next ESIG webinar on September 10th on system-level impacts of voluntary carbon-free electricity procurement strategies with Professor Jesse Jenkins of Princeton University. I'd also like to invite you to attend the ESIG Fall Technical Workshop in San Diego the last week of October, and I can assure you that you won't be disappointed. Further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Pete and Jack, I want to thank you again for this very timely webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.